So far, looking at binary, we've only been looking at unsigned binary, representing positive numbers in binary. We've ignored the fact that we can have negative numbers, and of course we've got to represent them too. So unsigned binary, what we've looked at so far, is just for positive numbers. In fact, the sign is kind of irrelevant because we know it's going to be positive. But signed binary can either be positive or negative, so we need to cater for a sign, basically. So there are quite a few approaches. There are two we're going to look at. The first one being sign and magnitude, which is the most logical approach, to be honest, because we've got to somehow represent the negative number, so like -5, we've got to represent the minus in our binary. So the way sign and magnitude works is the most significant bit, which is the left bit when you write out a number, the least significant bit is the furthest right bit, but we're talking about the left bit here. This is used to represent the sign, with 0 representing a positive number and 1 representing a negative number. So basically, if we wanted to store -27 as a byte, so 8 bits, with sign and magnitude, we would have our left bit, and the column headings obviously don't transfer to the computer, so these are just for our understanding. But the sign bit would be 1 because it's a negative number, so 1 represents a negative number, and then the rest of the number is stored as normal like you would. So the sign is the sign bit and magnitude is just the positive part of the number. So 27 positive. So this is just normal conversion which we looked at. So in terms of your process, you'll firstly look at the sign. If it's negative, you write in 1 for your most significant bit, and if it's positive, you write in 0, and then you can work out the rest of it normally, so the magnitude is filled in normally. So as I say, this is quite logical. It's the most obvious way to, I think, represent a negative number, just because it's copying directly what we do. So like -27, it's pretty clear what the translation is, it's 1-to-1. But it's not used due to certain processing issues. One of them, or the most obvious issue, being the fact that you end up with 2 zeros. You can have just a byte or any number full of zeros. So the left bit, this is saying it's a positive 0, and this is saying it's a negative 0, which doesn't make sense. 0 hasn't got any, it's not positive or negative, and anyway, it wouldn't really matter if you had like a negative 0, but it doesn't matter having 2 zeros, because how would you deal with them? It causes extra issues for people having to design the circuits. And there are other various issues associated with sign and magnitude, so it's not really ever used. The second approach, which is actually used by computers, is 2's complement. So there are other approaches, but these are just the two we're going to be looking at. So 2's complement is similar in the sense that the most significant bit, the far left bit, also gives us the sign. So if we look at it, so 1, we know it's a negative number, but the rest of it is quite different, and doesn't make a lot of sense unless you understand the actual method you have to go through. So first of all, what you'll do if you have to, say, represent -27 like we did before, you would write down the representation for unsigned binary, so the same for +27 essentially. Then you would invert every bit. So complement means to flip the bit effectively, so do not on every bit. So a 1 becomes a 0, a 0 becomes a 1. And this is actually called 1's complement. 1's complement is another representation, another approach, but is slightly weaker than 2's complement. So we basically flip every bit, and then we add 1 to it, and this of course would be done using binary addition. So basically, to sum up, you flip the bits and then you add 1 to it. There are 2 other methods I can think of, but I find this one easier. But if you want a shortcut, what you can do is you can copy the bits from the positive representation right to left until you copy a 1. So you write down a 1, when you get to a 1 you write it down, and then you flip the other bits, and this has the same effect of this. But I think this is probably easy to remember. You flip them and then add 1. Okay, let's do a couple of examples. First of all, let's do -35 into sign and magnitude. So positive 35, just to skip this, is going to be 1 0 0 0 1 1, and then let's just add 2 leading zeros on to make it a byte. And so this is positive, but we want it to be negative, so all we need to do to get this correct is just to change this to 1, our sign bit, our most significant bit, and the rest of it is normal. Let's now see how 2's complement differs. So first of all, we have got to write down our initial positive representation, but now we need to flip the bit, so that just means we're doing the opposite. So 0 becomes 1, 1 becomes 0, like that. So let's just get rid of this. So this is the invert stage, or the flipping stage, or the complement stage, and now we need to add 1 to this. So just 1, like that. Looks a bit weird, but this is just how it works. So this is very easy. 0 plus 1 is 1, as we looked at, and we can copy across the rest. So this number is -35 in 2's complement. So you can see how they differ. They're different numbers just because they're represented in different ways. Let's say we were given this result. We know this is -35, but let's just do the reverse process. So we basically need to subtract 1 from this. Actually, let me just get rid of this stupid border. So we need to subtract 1 from this, and binary subtraction is not particularly challenging, especially in this example. 1 minus 1 is 0, and then the rest of this is the same. Then we need to also invert it. The opposite of inverting it is to invert it, so we have to do this again. So flip the bits, and this is back to being 35. Let's do +4 just for completeness then. So for sign of magnitude, this is going to be 0, 1, 0, 0, this being our sign bit and this being our magnitude for 4. And it's the same in 2's complement actually. So positive 2's complement is the same as sign of magnitude. If we weren't asked to express it as a nibble, we could just write 1, 0, 0 in unsigned binary, but of course we can't do that because it looks like this is a negative number. Finally, let's just do 1, 1, 1, 0, whatever this is. In fact, let's do it as a byte. So we want this to be negative 14. This is currently positive 14. So to make this negative using 2's complement, we need to, first of all, in fact, let's do this by the copying method. So you start from the right hand side and you copy it down until you reach a 1. Then you write down the 1 and then you invert the bits. And this is 2's complement of minus 14. Just a few final points then. So in 2's complement, there's only 1 0, just 4 zeros or however many zeros. This is technically positive 0, but we can kind of deal with that. Only 1 0 is okay. And this, what would be negative 0 in sign of magnitude is minus 8, or in this example. So it's a different number, so we're okay on that front. There is an issue though, because of this imbalance, we end up with a range that is not quite normal. So we have more negative numbers than positive numbers because 0 is a positive number, so it's kind of taking up space for positive numbers. So that is something you have to deal with. So the reason why 2's complement is useful is you can do addition normally, so you can use the same circuits as you would for just unsigned binary. So you can, like in normal binary, you can get an overflow error you have to be careful about, but it may be more significant because the sign may change. So if you've got 103 in binary, of course, and add it to 115, this is going beyond what can be stored. So we end up with a negative 38 because the 1 is carried into the sign bit column. So we end up with a completely different number, and this is an overflow error. So it should be 218, but we end up with a negative number because it's carried and overflowed into the sign bit. And of course you can add negative numbers, so you can subtract using 2's complement. So like 31 plus 77 is 31 minus 77, and you get the correct answer. And similarly 6 minus 4 is 2, and you get the correct answer as well. So this is where 2's complement is quite flexible. So that's it, and as I said at the end of every video, make sure you do some practice yourself. There are converters online you can use to check the answers to questions you've kind of made up for yourself.